Oké. Excellent. Het gaat goed. Oké. Ziet er goed uit. Okay, students, welcome to the fourth lecture on Matlab in engineering mechanics. It's December the 3rd, 2020, and the topic of today is going to be least squares and zeros and roots. And that's chapter 5 and chapter 4 in the book. And now you would say, hey, why this strange order, 5 and 4? Well, I like to start with least squares, that's not so much work, and then do the focus on zeros and roots. Okay, I have to start the recording. Yeah, okay, recording has started. Okay, fourth lecture. So, yeah, let's start with an example of least squares. And the example goes like this. So suppose we have a set of data points, set of data points, and they come from measurements or whatever. It can be anything. So we have x values, and in this case it's 1, 2, 3, 4, 5. These can be seconds or meters or whatever. And we have measured values, that's y, I, oh that's not very nice, I, and that's a measured quantity, and well, we only measure up until 2 digits apparently, so that's 15, 20, 27, 35 and 40. And now our question is, can we make a model? Is there a model who can predict the data? To predict y as a function of x. Well, if we look at the data, then you will see that the increment in x is 1, right? And then the steps in y's are approximately, well, this is 5, this is 7, this is a bit less than, this is again 5, so around 5, right? These steps, approximately. So, yeah, you have the feeling that there is some sort of linear behavior between those. So a linear model would be, let's say we do a linear model. What would be a linear model? In this case, it would have the following form. Oh, don't zoom. Yeah. So we say then, well, the output is some constant plus some value times the input. So y is a times bx, a general parametric form of a straight line. And then if we look at our data points, you could say, oh yeah, 15 is a plus b times 1. And then the second one is 20 is a plus b times 2. 27 is a plus b times 3. 35 is a b times 4. And 40 is a plus b times 5. So the number of equations we now have is 5, right? And the number of unknowns is, well, we only have a and b, right? So that's a and b, this pair, so that's 2. Meaning that we have more equations than unknowns, and they are linear. So we cannot get these 2 values from these 5 equations. We have to pick 2 equations. So we take the first and the last, or we take the first and the second, or we add them up and then we do an averaging, or, I mean, you can think of a zillion ways to do that. But in essence, we want to say, well, we have our linear model, and then we can calculate what the difference is between our linear model, and then we want to be this error as small as possible. So let's try and formulate that. So what is the error with a linear model? The error we have is, of course, all these linear function values, which we can write as a linear function. We can write a matrix A times these two coefficients. Well, let's give them A and B, and that equals our output, our y, y vector, or in other words, A times these coefficients C is this y. And what does A then has as a form? Go away. Sorry, not the error. I will talk in the error for a second. Let's forget this. I can write these in a matrix vector form. So A times vector C is y, and the vector C is the unknown 2's. And what is in A and y are, of course, our measured values. So A then has the form. Oops, my pen. So A has this form. I look at the first equation. It says times AB equals, and then we have a right hand side. The first equation says 1 times A plus 1 times B, so I get 1, 1, and then here I get 15. Then the second equation says 1 times A plus 2 times B, I get 20, 1, 3, I get 27, 1, 4, I get, what was it, 35, and 1, 5, I get 40. So here you see this matrix A, these are the C's, and this is the Y, the Y linear from our model. And now we can formulate an error. Well, sorry, not a linear one. Now we can formulate an error. These are the measured values, sorry. And we can say, well, we can calculate this part, which we call Y linear. So Y linear is A times C. We still don't know what they are, but we can then say, oh, and then the error is apparently is my Y value, my measured value, minus my linear value. Still, we don't know what A and B are. And then what do we want? Well, we want to have A and B such, A and B such that, and now that the sum of the squares of these errors is minimal with respect to A and B. So we can formulate as an optimization, and we can say J is the sum of these errors squared, and that's an error I actually, or I. So that's the sum of this A times C minus my measured value. And we want to square that, and then we take what then we say, well, we minimize that with respect to A and B. So we do the dj dA must be 0, and dj dB must be 0. And from those two equations we then can solve what is A and what is B. So that is our strategy for the least square solution. So let's write that out. How does it go? Well, we can formulate J, because, well, we have our error here, right? That's in a matrix form, and then, well, in a matrix vector form it should be A, yi, and that's then, how do we write that? Well, transpose, of course, times this, because then we get the sum of all the squares of all these errors. And that thing we then now have to that is actually the error squared and the sum of that. And now we can take all these derivatives. So we say Jacobian already with respect to this thing. So we have to differentiate this with respect to C. So we get first differentiate this times this, and then keep this constant times that. So that's this becomes well, the only term here is, so that's A transpose times AC minus YI plus, and then we get this term AC minus YI transpose times A, and of course these two are identicals, that should be 0. So in the end we have the following conclusion. In order to be optimal, I get A transpose times AC must be equal to A transpose times YI. And from this I can solve my C's. So how do I do that? How do I solve for the C's? Okay, I have this matrix here, and although the matrix A, of course, in itself is a n by 2, number 5 by 2, then this matrix is a 2 by 5 times a 5 by 2. So in the end, that's a 2 by 2 matrix. And so apparently I can solve for that one. So I can then say, oh, C is apparently this A transpose A minus 1, if it's regular, of course, that's another question, times A transpose Y. And then I have my A and my B value, and then I can check how well does that fit. There is actually a very nice term for this inverse thing, this whole shebang, and we call that, I think, yeah, with the name we call it pseudo inverse. There's even a symbol for that. I think in mathematics you write it as E plus, and the name which goes by that is the Moore-Penrose inverse. In Matlab you can do either pinf of A, or you do A backslash. So there are two ways, but A backslash does a little bit different thing than pinf. I think that's also in the homework of this week. So to be precise, if you have this set of equations, A, C equals Y, then you can say, oh, C is A plus times Y, or C is pinf A Y, or C is A backslash Y. Well, the A plus you cannot do in Matlab, but these are two Matlab statements. So this is Matlab. These two. Okay, well, Matlab, let's do Matlab, right? Let's see how that all works. Okay. My notes. Oh, my notes. Nope, my notes. Matlab, where are thou? Here. Yeah. So, what do we have to do? We have to formulate our equation. Oh, yeah. That's funny. I always try to scroll. Okay, so we have our equations here. We have to set them up. So this is identities. These are all the x's. These are all the y's. So we have to form this matrix A and this vector y. And then from then on, it's all math, right? Then we have to form this A transpose A and A transpose Y, and then we can solve that. So that should be doable. Let's go to 100. So this is then the thing we have to make in Matlab. Yeah. Maybe I put it a little bit up here, and then we can look at it. It's my Matlab screen. Yeah, that's not so important for now. Yeah, let's start directly typing in a script file. That's usually handy instead of working at the prompt. If you work here at the prompt and you make an error, you have to go back with all your errors. So now we just type in a file. So that is a least square solution fit example. Yeah, I put my name in it. And maybe even also the date. I mean, it's good practice to do that always then in a standard way. And it always shows you that what is yours and what is others. Yeah, I was actually a bit pissed off today when I looked at all the homework assignments which were handed in. I saw some of you have broken the academic integrity, and we will get back to that. We will report it to the Board of Examiners, in the sense that some people copied homework assignments from previous years without mentioning. And to be frank, that's not the way to go. I mean, maybe you do that in kindergarten, but not at the university. We don't want that. We were very clear in the beginning about the rules and the guidelines. I don't want to spend too many words on it now. The answer is, don't do it. Follow the rules and the guidelines. Those who whom it concerns fit the shoe, right? Fit example, yeah, okay. Okay, back to more positive things. Least square solution, yeah, my typing is of course horrible. So let's start with the data points, right? Data points. So the xi's are, that was simple, just equally spaced, and the y's were, oh yeah, I can see them on the right hand side of my screen. 15, 20, 27, 35, 40. Of course you can wonder, does it look like a straight line if I look at the numbers? So why not plot them right away without doing anything, right? So plot xi, yi, yi, and we just want to have data points and not a line, because so let's run this. Run it. I said run. Yeah, okay. Okay. Oh yeah. Of course, errors, right? I'm very good at making errors. This shouldn't be right. Yeah, that's completely an error. It should be grid on. Okay. Let's throw this away. Let's run again. Okay, what do we see? Again, yeah, more errors. As I said, I'm very good at making errors. Okay. Yeah. Where's my figure? Yeah. Okay, we see these data points, right? Here. And yeah, they're approximately on a line, right? If I take a ruler and I keep the ruler, it's about, yeah, something like that. So that looks okay. Okay, so let's continue. Now we have to form these matrices, A and this right-hand side. Well, the right-hand side we already have. It's a row vector, but we need it in a column vector. That's no problem. And now we have to form this A matrix. So let's do that. So A equals, first the whole column with ones, and they should be the size of the axis, right? And then a second column with the axis. Well, why don't we transpose these here, and then everything is already done. Now a column with the xi's, and the yi's are already done. So now we have this matrix A. So let's see how that looks. Yeah. Yeah, this is the matrix A. That's okay. That's super fine. We can do that later on. Well, let's keep it. That's okay. Hold on. We're gonna maybe add some other stuff to that. So we have this matrix. Now we have to do this pseudo inverse thing, right? To form these coefficients. So what was the thing? We had to form these equations. A transpose times A is C is A Y. So if I form those and then solve for those, I should know what my C's are. Okay. Yeah, so actually my solution, right, C should be inverse of, well, let's first look at what form has the matrix A transpose times A. A transpose times A. Okay. So let's run this section. So we see, yeah, as we expected, a nice 2 by 2 matrix just filled with numbers, and well, it seems like it's non-singular, so probably I can solve that. So these coefficients C are then the inverse of this A2. Well, maybe I just keep this. So you have it in one line times, and then here we have to look times A transpose times y, right? So then we get A transpose times the data points. Okay, so let's run that. Yeah. We get two coefficients, 7.9 and 6.5. So these are the coefficients of the line. So those are the A and the B. So that is the constant one, and that's the slope. So now we can generate with those two numbers, we can generate the linear solution. So that's y linear is again this matrix A times C. So that's super simple. Now we have all the linear solutions. Then we can plot that on top of the old figure, so the old values and the y linear values. What are we going to use? We're going to use pluses or dots, or I don't know, dots maybe. Green, red dots. This was a blue cross, and this is a red dot. Yeah, so let's go here. Oh yeah, I should run the whole file. I lost my figure. Well, as you can see, the linear solution, well, we don't see that it's on a line. Why don't we add the line too? Let's add the line. So how do we add the line? Well, that is actually, well, we can take 2 points and draw a straight line, but we can also just say plot in red, and then we will get just a straight line, right? We now red, and then, yeah, we get a straight line. So let's throw this away, run it. Yeah, so we see our data points. These are the asterisks, the blue ones, and then we see our red dots, which is the linear solution, and we see these small differences. Of course, we can calculate what the errors is, and well, trust me, I'm a doctor. This is really the sum of the squares of these distances. These small distances, is really the minimal for. This is the best fit for that line. Okay, so that is the first part of our lecture, what I wanted to talk about. Let's kill this and let's kill this, and let's go back. So my first part, as I said, was this these squares part. And please read chapter 5 in the book, and I think there are 2 assignments on this in the homework. I don't know by head, but check it out. Yeah, the second example I like to do is for the zeros and roots. So, yeah, where's my pen? So now we do zeros and roots. So where are my roots? So again, that was chapter 4. And then the example I like to do is a spring-loaded inverted pendulum. Spring-loaded inverted pendulum. What is that? It so happens that I have one. So this is an inverted pendulum, right? If I keep it on my hand, I can balance the thing on my hand, and it's very unstable. It will always fall over, right? If I put that on my hand, maybe I should zoom out. Well, anyway, it falls over. Very unstable configuration. So what can you do? Maybe I should go back a little bit for the demonstration. So yeah, so you can balance it. But what you could do as balancing, you could add a controller here, and the controller is my hand. Well, what does my hand do? It is a certain stiffness. So the moment the thing starts to move in this direction, my hand supplies a torque. Or if it moves in this direction, my hand supplies a torque. So gravity is pulling on the one hand side, but my hand is giving this restoration force. So that is spring-loaded. And by this spring-loaded, I can keep it in this position. If the spring is very weak, it will find another equilibrium position, right? It's a very weak spring. So, we have to crank it up, and we're a weak spring here, fine, probably this, or maybe this, whatever, depending on the spring. And now we want to know, for a very stiff spring, of course, the equilibrium condition is somewhere around here, but if it's a very weak spring, or even weaker, who knows? A very weak spring is maybe this. This is a super weak spring, right? And so there are a whole number of solutions for this equilibrium for different spring stiffnesses. So that's the problem, and what we want to find is, given the spring stiffness, what are all these equilibrium positions? Okay, so how do we go about? So this was the problem, right? I had my open hand, and then on top of that I was balancing this inverted pendulum, so that is the inverted pendulum part. And then the spring-loaded one is that I then add some stiffness here. That's the spring-loaded one, by keeping it a bit tight. Okay, the model we have. So we usually make models of this. The model for this is, then we start drawing, right? What do? We have some support here. And now we have some stick. Something like this. And it has a center of mass here, M. And that's at the distance L. And there's gravity going on. And then we have some coordinate, phi. And and we have, of course, this spring. So we have to, then we have to connect it to the ground, and then the spring stiffness is, let's say, K. So at the distance M, L, we have a mass M, we have gravity here, we have a spring stiffness, and we have some coordinate. Okay, if we want to know about equilibrium and so on, then equilibrium is equilibrium. Wow, come on, guys, let's do it properly. Equilibrium is about finding the equations of motion, right? And then assuming that all time derivatives are zero. So that's saying phi dot and phi double dot is all zero. And then we can find the equilibrium. So how do we find the equation of motion? Then we need some instrument, and I always say the most powerful instrument we need is, what do we need here? Every engineer has this thing, right? Scissors. So what are we going to do? We're going to, with the scissors, we will be able to cut the system loose from the environment. So we use our most powerful instrument, the scissors, we cut it loose, and then we get a free body diagram. And this is then a free, oh, that's not nice, come on. And here we get the free body diagram, so we have our body isolated, we have forces here. Of course we also have, we cut it through the spring, so we also have some torque here from the spring. So we have an ms, right? We have a fx, we have a fy. Remember we have this angle, phi, and we have at the distance, and we have gravity here, mg, we have to put in all the forces. What else? Oh yeah, this distance is there, L. And then I think the figure is done. So we have a horizontal force, a vertical force, Fx, Fy, we have a torque from the spring, we have a gravity force, and we have some geometry. So then we can do all kind of equilibrium things, and actually a quick and dirty way, if this is the support point P, then a since P is a fixed point, so P is fixed, is fixed, and therefore we can say that the sum of the torques about P, should be the mass moment of inertia times P times the angular velocity. Of course, if you do it the proper way, you have to set up the three equations of motion, two Newton equations, one Euler equation about the center of mass, and then you can solve for those three unknown forces, and finally in terms of this one variable. But I do a quick and dirty way here, and you should not do that. That is always confusing, but you can, around the fixed point, the sum of the torques is mass moment of inertia times angular acceleration, and then that angle is the generalized coordinate for the system. Okay, sum of the torques, well, we already have by phi defining in this direction, we have a plus definition actually for everything, so this is what we call plus. So looking at that sign, we can say, okay, take all the contributions. So first we take the contribution of gravity, so that's mg, and then the arm is L sine phi, and it's plus, right? And then the spring is counteracting this phi, so it's minus k times phi. That's the spring. And then that should be equal to the mass moment of inertia around point P times the angular acceleration. Then equilibrium. What is equilibrium? As I said before, that's phi dot and phi double dot is 0, or in other words, equilibrium is expressed by mgl sine phi minus k phi is 0. So here from this we can find the equilibrium position, so this guy. Now we have a variable that is our angle phi, that's the one we want to solve. So from this we find all these phi zeros, all these equilibrium positions. And equilibrium positions, it's not really a position. But we also have a set of parameters in the problem, parameters. And the parameters in our case are the mass, gravity, length, and the spring stiffness. So we have 4 parameters. Now that means if we want to investigate what is the equilibrium value, then we have to do that for all these four parameters. That's a lot of work, but we can do scaling. Because we have physical quantities, this is the dimension of this is length, right? So that's meters, so the dimension, meters, this is meters second squared, sorry, this is kilograms of course, meters second squared, this is meters, this is Newton per meter. So we can do scaling because we have length, mass and time. Here we have the mass, we have the length, and time is hidden into gravity acceleration. Things on the moon, you can jump higher on the moon than on Earth, well, whatever. So now my scaling, I do it a quick and dirty way. I take m equals 1, l equals 1, and g equals 1. And that means I'm able to scale all these 3 different physical quantities. By the way, your time scale then is something with square root L over G or something like that, right? With a real L and a real G. Anyway, if we do the scaling, then we can get rid of 3 of these variables, and we are stuck with sine phi minus k phi is 0. And now we only have one parameter, and that is the scaled stiffness. That's a non-dimensional stiffness. And this is the equation we want to solve, and that is now finally where we come to roots and zeros, because we want to know zeros of this function. That is the thing we want to solve. Now, since it's a very simple one, we can make a graphical interpretation of this already. So we can draw two graphs. We can draw the sine graph and the k-phi graph, and all the points where they are identical, that is where this holds. You could also say, oh yeah, sine phi equals k times phi. So this was the gravity torque is equal to the spring torque. That makes sense. So that's the restoration torque, and this is the gravity torque. Okay, what does the graph look like? So first let's draw the sine phi. So that is simple, right? That is this nice wobbly function which goes between 0 and 1 all the time. So 0, so this is phi, this should be pi, this is 2 pi, 3 pi, etc. And then the height of this is 1, and the lowest is -1, right? So that is the sine phi part. And then k times phi, k times phi is just a straight line from the origin, and let me just draw this. This is k times phi, for some k, where the value of k is of course the tangent of the function. And if k is very large, then you have a line like this, so that's k very, very large. And if k is very, the spring stiffness is very low, then you have a line like this, so if k is very, very small. And small and large are just order 1, that's the beauty of scaling. Okay, so then we have to solve this nonlinear equation. So given some k, so for instance, suppose we start with k equals 1/2, for various k's, solve sine phi minus k phi is 0. For instance, you want to solve sine phi minus 0.1 times phi is 0. So how do you do that? Well, this is a nonlinear function, right? Which we then have to solve. And I guess we have to use Matlab for that, right? So let's go to Matlab. Okay, Matlab. This can be a bit bigger, yeah. Okay. Yeah, so let's first clear our, well, the equation we have to solve is super simple, right? But let me put it here. Let me clear all the commands, and yeah, I did everything. Command history. In the workspace, yeah. Okay, so then all my variables are gone. So now I start with a clean slate. So I take a script, and we put this over here for the time being, and we see what we're working on. Oh, not that this one go away. This is the thing we have to solve. Solve non-linear equation. It is still 3 December. Yeah. Was a spring loaded inverted pendulum problem. Okay, and the equation is sine x minus k times x is 0. I use x here because there's no Greek phi on my keyboard. Okay, and let's say we start with k is 0.1. So then the question is, what is the solution? Well, if we look at the graph again, then of course, for irrespective of what k is, 0 is always a solution, right? There's always And all the figures start at 0, and for phi is 0, this is 0, and irrespective of k, this is also a 0. So the zero solution is always a solution. But we are interested, of course, in these type of solutions, right? And so how do we find them? Well, there is a thing called f0, a function f0, and then you have to give a function and then some start value. So we can use f0, and the first parameter is we have to give it a function, and you can either be a function which is an M file, or it can be a zillion ways, but you can also type the function just as a string. So in our case the function would be sine, and I use x, then it will understand, oh, x is probably the independent variable, 0.1 times x. So this should be the function. Well, and then we have to give it an interval where probably the solution is. Well, I know around 0 there should be a solution, right? So -1 and 1. So let's look in this interval what the solution is. Okay, so let's run it. Let's save this. And the answer is 0. Yeah, I'm totally happy with that. That's the solution, right? Around 0, if we look at it. Yeah, that's good. But we are actually seeking, are there more solutions? For instance, maybe around pi there's a solution. Yeah, it's very nice, but I don't want to see this WhatsApp in my screen here, so I quit it, sorry. Okay, so I want to find these other solutions. So how do I go about? Well, then you just have to give another interval. So say we want to know it around pi, so we take pi minus 0.2 and pi plus 0.2. Maybe there's a solution, who knows? Let's run it. Oh, what happens? Function, it must, yeah, that's interesting. Function values at the interval endpoints must differ in sign. Yeah, so apparently there is no 0 there. So let's be a bit broad. Let's say we want to know between pi and 5 times pi. There must be something out there. Let's run it again. Oh, again. Must differ in sign, so we take half pi. Yeah. Now it finds a value, 2.8523. So 2.8453, that is somewhere apparently here, right? So apparently it finds a solution there. And are there any more solutions? Is there anything above that? So let's say 2 pi or... Well, we can easily check that, because if we put in 2 pi and it goes above 1, then there's probably no solution anymore. So 2 pi is something with 6, right? And then times 0.1, oh yeah, that's 0.6. So maybe there are more solutions between 2 pi and so 2 pi and 3 pi, something like that. Who knows? Where's my thing? Yeah, doesn't find anything. Yeah, anyway, this is how you slowly seek for solutions. You show this, you change the intervals, and you seek, are there any more solutions? However, if you look at the problem, and therefore we go to my notes again. If you look at the problem, it's actually that simple to solve it. So because instead of saying given some, so this was the problem, sine phi minus k, phi is 0, you can say, oh, I give a k I can solve for phi, but you can also turn the thing around. You can say, oh, apparently k equals sine phi divided by phi. So, meaning I pick a value of phi, and that's then my equilibrium value, and then I can calculate for which k is that the equilibrium value. And then I can plot those. And then I can plot all the different values which go by that k value. So let's do that. So now we just start with all these phi zeros, and then we're going to look what are the k's which result in this equilibrium condition. So let's again do that in Matlab. Yeah. So here we go. Oops. So for that we generate just a whole. So for now let's forget this. We now generate the whole set of angles, so we call that this x, well, maybe we should call it phi. It's not sort of dirty. Let's call it phi. That makes it better. The code is better to understand. Then we say phi equals, well, we make a linear space out of that, and it's phi 0 actually, because it's all these equilibrium conditions. And then we start at 1, and then, yeah, I don't know how many do we want to see? We want to go to 12 pi or something like that. I don't know. And then we take 501 points, something like that. So we now have a nicely equally spaced phi, and then we're going to calculate our k values, the spring stiffness value which goes by that equilibrium angle, and then that is simply sine phi 0 divided by phi. Oh, we will have to do a point divided because we want to do element by element, and then we're going to plot as a function of these variable k's. K on the horizontal, and then we want to know what equilibrium angles go by that. Grid on, and then maybe we label k value. No, that's x label, sorry. X label, is that correct? Y label, well, we'll see if it's correct. Equilibrium angle, and we're going to say phi 0. Let's run that. Okay, now we have to think. Actually, I was sort of stupid. And why was I stupid? Because I programmed something, I ran a code, and I had actually no idea what to expect as output. And that is a bit not so smart. If you do it, you should actually say, okay, if I do this, what do I expect? So before executing this, I would think about, oh, what type of graph do I expect? And then you would say, well, I would expect if the spring stiffness is very high, then there's only one solution, like phi 0, right? Yeah, that's what I expect. And if the spring stiffness is very low, I expect a whole bunch of solutions. And how does that go? Well, again, if the spring stiffness is very high, there's only one solution. I mean, what else? However, if the spring stiffness is low, and maybe very low, and there's a very weak spring, I can turn the spring like once time around, like your watch. Well, you don't have those watches anymore. I do, but spring loaded. You have to turn the spring a couple of times, and then finally you have, here the restoring force of the spring is just enough to keep it in this position. So you went a whole couple of times around, so phi is really large. So that's a weak spring. So now we know what to expect. So let's run it. So what do we see? Well, for a high k, the k is even limited to 1. Even higher, there's only for case 1 there's only one solution, and that is 0, and for higher it's always 0. And then when the k goes down from 1, you get other solutions, right? And here you see, for a very low value of k, I have a whole bunch of solutions. So here, so maybe we can draw a line, and we can insert a line. Yeah, I can do that. Oh. And not only the YouTube is laggy, but my Matlab is also laggy. So here, if I draw a line here, then for this k value, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and it could, like a 20 solution. So but you can wrap it up, and every time you find an equilibrium solution. Now, I talked about positive k's. There are also negative k's. What do they mean? Well, a negative k is that you give some angle, and then it's like an unstable spring, and those things do exist. I mean, it's one of the solutions here. Now, what is a negative spring? You can build it. So there's no restoring force. The restoring force is not restoring, but just going the other way around. So, for instance, if I make this contraption, I have this thing and I have a bar, and if I put, for instance, a spring, if I attach a spring here and I make it tight, then it will go back, depending on the spring, it will pull it back. However, if I put the spring here, then a small deviation of the bar will pop the thing out. So this is like a negative spring. So this is the way to make a negative spring. So yeah, negative springs do exist. That was the bottom line. Okay, so as we've seen here, for a very weak k, I have a whole multiple set of solutions. And how do I find these solutions? Well, you can do it either by doing fsolve to find discrete values, or if you want to show by accident, this is a very simple problem. Usually the problems are not that simple. I still have, I wanted to talk for an hour. I still have like 7 minutes, and in 7 minutes I like to demonstrate another thing, and that is the following. And then we go back to this. So let's pick like this case. So we have a solution here which is very close to pi, which, by the way, you can see in this graph. That all these values, of course, they are multiples of pi, of course. If you divide this by pi, then you will see, there are multiples of pi. That is going around a number of times. To see that, maybe we should go in the code, and instead of plotting phi 0, we can plot phi 0 divided by pi. And then we should say that in the text too, divided by pi. Now, why do I use the backslash? Because then I nicely get my Greek symbols. It's a LaTeX formatting thing. So let's get rid of the figure. Yeah. As you can see here, this is a phi, and here a pi. And so I can get these symbols, but only in the graphs, not just in the code. And then you see these multiples, right? 2 pi, 4 pi. For k is 0, these are solutions, because that is hanging down and then standing up, hanging down and standing up. So the k is 0 solutions here are exactly these solutions. So being straight up, or that's the 0 one, or being straight down. So the 0 one is here, so that's this one, straight up. And then the next one is here, for etc. Sorry, here, pi, 1 pi, then here again up 2 pi, 3 pi. Well, I can go on forever. Now, you can imagine that from some of these equilibrium positions, you know on forehand that they are unstable. So let's talk about the k is 0 one, there's no spring. I know, for instance, that the first first solution with pi, this one, is a, well, the first one is actually this, but that's a limit case, right? Because sine phi over phi, well, anyway, and I'm not going to talk about that later on, maybe, if time permits. Anyway, the first equilibrium solution like this, that's very stable. But then the second one, 2 pi, that's like this, that's an unstable configuration, right? And maybe even with a finite spring, like this one and this one as a solution, we don't know, are they stable or unstable? Because in the zero solutions we get alternating stable, unstable, stable, unstable, stable, unstable, etc. So you see, it is equilibrium, but we can even distinguish the equilibrium as stable and unstable. Now, how do we do that? Well, then we have to look again for stability. We have to look again at our equation of motion. Yeah. So our equation of motion being this guy, but actually being this guy. And then we have to look around the equilibrium for small changes. So we have to linearize around the equilibrium. Now we can do that if this is for stability. So we want to know stability of the equilibrium. Equilibrium phi 0. Well, then we linearize around phi 0. So meaning you say phi is phi 0 plus delta phi, and then of course phi double dot is then phi double dot 0. Well, it's constant because that's a 0, right? Plus delta phi double dot. You just fill that into the equation, and if you do that, then what do you get? You get the linearized equation of motion. So we get in the end the sine of phi 0 plus delta phi minus k times phi 0 plus delta phi equals mass moment of inertia delta phi double dot. Well, for this we want to linearize this, and if we linearize that, that's approximately equal to cosine phi 0 times delta phi. All the other higher order terms disappear, and of course it's a sine phi 0 plus this whole term. So let's do it properly. So this is sine phi 0 plus. This is then the derivative of this one, sine is cosine. That's the Jacobian times the delta, and then minus k phi 0 minus k delta phi. And then, lo and behold, of course, this is equilibrium, so meaning that 0, and remains is our cosine phi 0 times delta phi minus k delta phi is y p delta phi double dot. And now we have a nice differential equation with cosine phi 0 minus k times delta phi is ip delta phi double dot. We assume these exponential motions, some constant times e to the power lambda t. If we then substitute that, we get our dynamics equation. So we get our characteristic equation in that sense. We get we have to differentiate this twice, so we get 2 times lambda. We get lambda squared equals cosine phi 0 minus k divided by ip. So lambda equals plus or minus the square root out of this thing, cosine phi 0 minus k divided by ip. And then the nature of these solutions determine is it stable or unstable. Well, since you have plus and minus, you have a minus, but you always have a plus. So if this cosine phi 0 minus k is positive, it's always unstable. But it can also be negative, of course, this cosine phi 0 minus k. If it's negative, then I get these solutions. Then I get plus or minus, and then I have to change that make it positive again, and then times I, so I get oscillatory solution, oscillatory stable solutions. So this is the stability condition. This is that the thing is stable, that the solution is stable. So you can then investigate for all these solutions. You plug in your K, you plug in your phi 0, and then you see, oh, well, is this a stable or an unstable solution? Or in other words, if we then go back, and that's again a nonlinear problem, if we then go back, then you can take, for instance, this point, and then you can say, okay, this is then my phi 0, and now I can calculate, is it stable or unstable? Well, you don't have to calculate it, you can already see it a little bit from the graph, if it's stable or unstable, because the restoring force of the spring goes like this, whereas the force from the gravity goes like this. Meaning that if there is a change, then gravity becomes a lot bigger than the spring, so this is probably an unstable solution. However, here you have that the gravity is restoring with respect to the spring, so this is probably a stable one. So you can then characterize all these different routes as being either stable or unstable. And again, you can write a script for that, and you can then distinguish between all these different routes. Finally, I like to share that script where I do that with you, and I will also share that on the website. So let's clear the commands again and clear the workspace. So we start with a nice clean slate. So here I have my inverted pendulum example, and I show it because then because there's a lot of text in here, and I show it because it also shows how to find solutions, how to plot things in a nice way, etc. So let's run it. Let's run the first part, and the first part is just what we did in class, only now I turn the whole thing around. So on the horizontal axis I have these equilibrium angles, and vertically I have the spring stiffness, and I say actually, well, for phi is 0 every spring should do, because it will always give an equilibrium. And then we see all these solutions. That's the first part. Now we want to look at stability, right? So that is the second part. And then for stability we already found this condition in our derivatives here. So we already found the condition here for stability, k larger than this cosine phi. So here we go. K larger than this cosine phi. So then we can plot that in our figure. So we plot, so this was already a plot of the k, and this is just a plot of cosine phi. And everywhere where cosine phi is, where k is larger than cosine phi, the thing is stable and all the other are unstable. So this branch should be like a stable, this is an unstable solution, stable solutions, unstable, stable, unstable, stable, unstable. So, and what does that mean? Well, it means that if it's like this with the spring in this position, it's a stable one, and if it's like if this is like this, it's an unstable one. Sorry, and if it's like this, then it's a stable one. Around this, it's a stable one, and around this, it's an unstable one, etc., etc. And that's what you can see in the graphs. And then finally, of course, you want to find exactly what are these crossings. And these crossings is, of course, again a solution of a problem where you say, oh, I have to solve both equilibrium condition and this stability condition. I want to know what is the boundary. So then I have a problem which I have to solve, and that is a double problem. I have to solve sine phi 0 minus k phi 0 is this, and the other equation we have cosine phi 0 equals k. And that's something I have to solve then. Phi 0. So then we find all these crossings, these points, where it changed from stable to unstable. Find from stable to unstable. And again, these are two nonlinear equations, and I can fiddle a little bit with it because this k is linear, so I can put the k in here, and actually you can then see sine phi 0 minus cosine phi 0 times phi 0 is 0, or in other words, I have the following equation: phi 0 equals tangent phi 0. And that's again a nice set of nonlinear equations which you can solve. If you graph that out, and these are the asymptotes of tangent, so tangent goes like this, and again, and then the function phi 0, which is just a straight line, goes like this. And then we have one solution, two solutions, three solutions, etc., etc. So you can find all these solutions. And those are exactly the points here in the graph where it changes from stable to unstable. Then if you have found those, then you can characterize those, and then you can make those pieces of the plot give it a different color, or what happened, guys? Where's my feeder? Yeah, within the section, advance. Oh, yeah, here we see. And then you can run this and find all these crossings. Well, we only look at positive. We only look at the positive k values. I discarded all the negative k's here. So I only look at the top part, and then we see, oh, these are stable solutions or unstable solutions here. So this is these are all solutions. This is unstable, stable, unstable, stable, where these points we have determined with a sine phi, cosine phi. I will post this thing on the website, and then you can have a look at it, how I do with the plots and the different colors, different light types, finding all these zeros, and of course using this f0 function, which you can do for a scalar function. You can also do it for more equations and more unknowns. Well, read all about it. That's homework. I like to wrap up now. I keep the streaming open, I keep the recording open, and I will go to my Zoom session. Okie dokie. Yeah, and then we can come in Zoom, and I put Zoom here. Yeah. Then Zoom is in the recording, and I say show participant, or participants will come. So now we can do questions and answers in Zoom. Oh, I get totally fed up with this camera stuff. Yeah. Okay. Double me. I am double me. So please come to the Zoom. And what is the Zoom address? Yeah. I can show that. I can show that is easy. Meeting information. Yeah, now you have the meeting information. So, oh, no, you had the meeting information. So this is the Zoom address. I can put that in the chat. Yeah, that's sort of smart. Okay. Yeah. So please come to the Zoom. And what is the Zoom address? Okay, dan moet ik dit even. Ja, gelukt. technique. Hi.
Hello, this is about the integrity statement. So is it? It's a little unclear what has happened.
I can put that in the... Wacht even hoor. Ja, that's okay, but I'll kill this, then we don't have a double voice. Hopefully. Okay, yeah. How's the sound now? No echoes anymore? Oh, there's no sound. Yeah, there is sound. I see sound. Can somebody say something?
Yeah, I can.
Yeah, okay, perfect. Yeah, thanks. Yeah, I had an echo from all the different screens which are open. Horror. Questions? Any?
Yeah, so what happened concerning the integrity statement? Is it you were allowed to cooperate, right?
Yeah, you're allowed to cooperate, you're allowed to use code, that's all no problem. However, you're not allowed to copy things and then say nothing about from whom you copied, that you copied and from whom. So I discovered that some people just copied from previous homework assignments because, well, they're not exactly the same, and then some students are even that stupid that they just copy from a last year and don't check if maybe this year is a bit different than last year. So in that way they fall through the month, right? But that's not the idea. It's okay to use work by others. I have no problem with that, but then say so. That's in the rules. And if people say, if they would have said, oh, I have no time, so I copied the answers from last year. Okay, but if they say nothing, then it's suddenly academic integrity, and I'm going to mention it to the Board of Examiners. As simple as that.
Okay.
Is that clear?
That's clear.
Yeah.
Thanks.
So if you follow the rules, there's no problem.
Don't agree with the comments that were made on your work.
Again, sorry, I was talking while you were.
What do you have to do when you don't agree with the comments that were made on your...
Oh, well, therefore you have this reflect on the review. So you just write that, and if that gets stored, and then we have that in our system.
Okay.
And then in hindsight, Rosanne and I, we are looking at the different scores. So if we see that the three reviewers agree approximately, then it's okay. If we see one outliner, we say, hey, what's going on here? So that's one flip of the coin. So that's for the guy, for you who will get the grade. On the other way around, we also look at graders. Some graders do 10, 10, 10. That's not the way to go. So then we look, how are the graders doing? Are you taking every work seriously, or just finishing up quickly? So there are two ways we look at the work, but it takes time. So there's a bit of a lag in feedback on that.
Okay.
I also had a question.
Sure.
I was looking on Brightspace, and it seems that this time in feedback fruits we do not have our assignments to give peer reviews on. Yes.
So, really?
Yes.
Yes. It says feedback by teacher and not feedback by peer review.
Yeah, I have so many trouble with feedback fruits. Like your grades are also not in the grade book. Okay, so specifically, so for homework 3,
yes,
there's something wrong, and what is wrong? Homework 3.
currently you have to give all the feedback instead of via peers.
Okay, 3 feedback pairs. Okay, are missing. Yeah, I have to fix that ASAP, right? After this Q&A session, I will see how I can fix that. Yeah, thank you.
No problem.
Well, it is a problem, but yeah. Other questions? All quiet on the Western Front.
Hello.
Yeah.
I had a question about homework 3. Can I ask it now?
Sure.
So the question is about how to keep those Starling point, which was mentioned in the question. There is one second. Let's read the question. Yeah. So I need to find a star-like, a point on the palm which is star-like, and I could not find that. Could you please maybe help me get that?
Well, first you have to help me, because homework 3 was a number of assignments and I have no clue which assignment you're talking about.
Can I maybe share the
Yeah,
question?
I think you can share the screen, right? I think I allowed. Yeah, so please share the screen and
Yeah.
explain.
Yeah, I was just solving this question, but I was not getting the answer for the center point of the XY coordinates, which
Yeah.
has to be star-like
Yeah,
in this question.
yeah.
So could you please help me with that?
Yeah, let's see, how can I address that? So if you work with, well, if you seek a function, then you want to have a single valued function, right? Meaning that for a given angle, you only want to have one radius. Okay. Now suppose you take the center or if you have your hand, and you take the center somewhere out here of where the angles start, where the origin of the radius is. Then you see, well, if I take a radius, a fixed angle, I have 1, 2, 3, 4, 5, 6, 7, 8 radii. So I have a multiple valued function. That doesn't work for curve fitting. I mean, in the curve we assume it's a single valued function. So now what do you have to do then? Then you have to think, oh yeah, I have to find a point where the rays are such that it's single valued. Right? And that shows that it's not so easy actually.
Yeah.
That maybe even impossible for your head. I don't know. It can be. I don't know. Probably. And it has to do with convex and convex shapes, and that's all higher math, and I have no clue about that, but yeah.
Okay.
Yeah? So therefore you have to do a little bit shifting of the origin to make sure, that, oh yeah. Okay, does that answer your question?
Yeah.
Great, okay. Yeah, please unshare, and then you go back to the crowd. Okay, any other questions? I have a question for you then, if somebody can answer it. I cannot see feedback fruits as a student. I can see it as a teacher, but not as a student. Now for homework assignment 1, we are done with everything. And so the review is done, the grading, etc. And I said publish the grades. So it should be that you see a grade. So my question to you is, do you see your grade for homework 1 in feedback fruits?
Yes.
Okay.
I can see it.
And is that then an average of the 3? I have no clue what you see.
Yes.
If somebody,
I believe.
yeah. if somebody can do me a pleasure and just send me how does it look for you as homework 1, the grading screen.
Maybe I can share the screen again.
Yeah. Oh, it's a privacy thing, of course, and if you don't want to, then okay, but that's great. Okay, so you get really a total. That's good. Or is that per reviewer, or is that average over the 3?
It's shown in total.
It's average over the 3 reviewers, right?
Per part. So this is the ratings, and this is the other feedback.
Yeah.
Reflection part.
Yeah, but the 7.4.2 is it's averaged over 3 graders.
Yeah.
Great. Yeah. Okay. So then we know what to do. But you also see the individual ones. Oh, that's average too. And then what do you see? But you should see 3 comments for every section then, because there are 3 reviewers. Yeah, with all these fruits, of course. Horror. Okay. Yeah, thank you, banana. I don't know what you are. Yeah, cool. Yeah, thank you, Nick. That's clear. Yeah, that was my question. Yeah, and are you happy?
I wasn't very happy with my last check because I got the feeling that one person in particular didn't take the time to check my report because he stated things
Yeah, very good.
that weren't simply true.
Yeah, okay, that's very good. So you put that. That's a reflect on the review, right?
Yeah.
Write that, and Roseanne will pick that out. We'll find that. If you use chocolate letters, capitals, then it will really stick out. And then we will go through those reflects. Yeah, great. Yeah, but yeah, on the other hand, I'm sorry for that. It's just like in real life, huh? Peer review.
Yeah.
Sometimes life is unfair, and yeah, that happens here too, and it shouldn't happen too often. So
It's just a little frustrating.
it is, yeah. Life is too sometimes, yeah. But we'll do our best, yeah.
Well, that's it from me then.
Okay. Well,
Thank you.
yeah.
See you next week.
it was my pleasure. See you next week. That's the last one then, eh? Yeah, this was 4. 5 is the last one. Yeah, okay. Yeah, because it's only 2 ECTS, so yeah. Okay, guys. Well, keep up the good work, and then I'll see you next week. Yeah, I'll just wait until everybody's gone, Sandeep.
Bye.
Yeah, okay, bye.
Sir,
Yeah.
I did not do my Matlab assignment this week.
Yeah.
So, should I do the feedback, or do I get?
No, you if you haven't done it, you will also not get a review request. So
Okay.
you only get that when you hand in something. But this week everything went wrong, so apparently I have to do all the reviews. There's a switch which is wrong. Well, I'll try to fix it. But if you did not hand in, then you cannot do a review. You have not.
Okay.
You cannot. Yeah.
Yeah.
Okay.
Yeah. Thank you.
Yeah, you're welcome. Take care.
Bye.
Bye.